So today we'll look at rates of change, which essentially is what our derivative is. It measures a rate of change. The steeper the curve, then the faster the quantity's changing. There's my random graph which I've done. The first one there, so at the point P, we know, well, if I was to draw in a tangent, it would have a positive slope. So we know the derivative would be positive. That's where we say the curve's increasing. Then we get to the top, so Q, and the tangent's horizontal, and we say the curve is stationary. It's not going up, it's not going down. And then we come back down, and at R, now the tangent's negative, and so that's where the curve is decreasing. PQ, I've got two different points on the curve here. So if I draw a line here, so I've drawn a secant. A secant is a line that cuts a curve in two spots or more, as opposed to a tangent which touches it in one spot. But if I was to find the slope of the secant, that gives me the average rate of change between those 2 points. As opposed to over here, a single point, if I was to find the slope of the tangent, that gives me the instantaneous rate of change. And usually that's a lot more useful. Like, imagine you're driving along and police pulls you over and he says, mate, you're speeding, and you go, no, my average speed was okay. Now, he won't wear that. I mean, it's the instantaneous speed is interesting. All right, so let's have a look at this example. We've got a water tank, which is emptying out. Q litres of water is the amount of water that's in the tank at any point in time. And we've got this function here to work out what the volume would be at any particular time. So they want to know, at what rate is the tank being emptied? So how does the volume or the quantity change with respect to time? So in other words, what is the Q to T? So we differentiate it like normal. This one, anarchy. Bring down the power, lower the power. And you notice I get a negative. Negative tells me it's decreasing, because that tangent would be going down. So how much time does it take to empty the tank? Well, we know the tank's going to be empty when there's nothing left in it. So Q would equal 0. So we know it takes, 20 minutes it would take. At some point in time, it will be emptying out at the rate of, how many zeros are there? That's 20,000 litres per minute. So when is that? So when is the derivative? We want the instantaneous change to be, and it's flowing out, so it's decreasing. So we want it to be negative 20,000. So we solve the derivative equals negative 20,000. And we got after 10 minutes. But what's the average rate at which the water flows out? Well, if it's in the first 5 minutes, I need to know how much there is initially, so sub in t equals 0, and how much there is at t equals 5, and it would be the slope of the secant that joins those two. So, well, I was going to say y minus y1, but I suppose in this one it's q2 minus q1 over t2 minus t1, and we get minus 35,000 is the average. Let's look at something, is it right to say a bit more interesting? Yeah, possibly. But one of the main things we use all this rates of change for is motion. That's one of the original reasons calculus was thought of, is because they were trying to work out planetary motion and things like that. So, a little bit of history here for you. So calculus, you may or may not realise, was independently discovered. So around about the same time, two different people came up with a similar idea. One gets all the credit, whereas the notation we're using actually belongs to the other. And here's the other. Gottfried Leibniz. He was 28 years old when he came up with the idea. But it's his notations that we use for calculus, so the long S symbol for the integral and things like that. And the other one who gets all the credit, of course, is Isaac Newton. He gets the credit for everything. How many things are named after Newton? But he was only 22 when he thought of it. Oh, the dot notation. We haven't looked at the dot notation yet, have we? So it's another way of writing the derivative is with the dots, but usually that's just for motion when you're talking about motion. So displacement, velocity, acceleration. What are they? Displacement, we tend to use x because we think of moving along the x-axis. In science they use s, don't they? Makes sense because displacement begins with a D? Well, why would they use S? I'm trying to think of a logical reason for using S for displacement. Displacement. I don't know. Displacement is basically distance with some direction attached to it. So now that the plus and the minus of the number has more meaning. It gives it direction. Velocity, so V obviously for velocity, there's the x dot notation I was talking about. So the first derivative, because velocity is the rate of change of displacement with respect to time. So it's speed, but with direction. So it tells you in which direction you're travelling as well. And then acceleration, well now we've got all sorts of notation we can use for acceleration. Acceleration is the rate of change of velocity. So we could use A for acceleration, but it also means it's the derivative of velocity. But if it's the derivative of velocity, it's also what we call the second derivative of displacement, so differentiated a second time. So let's have a look at some curves here and how they sort of relate. Here's a random displacement time graph I've drawn there. When the displacement graph is stationary, so it's got a stationary point, so for instance there, then I know the velocity must be 0. Kind of handy we call them stationary points because that ties in quite nicely, doesn't it? Velocity equals 0, it's stationary. So then I could plot that on the t-axis of my velocity graph. And there's another one over there. So again, that's why I like to draw these graphs underneath each other because then I can just translate the information down. When the displacement graph is increasing, well, that's telling me the derivative must be positive. Well, the derivative is velocity. So for that area there, velocity will be somewhere above the t-axis. And then after that second dot, our curve is also increasing, so velocity would also be positive. Similarly, when the displacement graph is decreasing, so in that section there, then velocity would be negative. So we're in there. The velocity graph is stationary there. How did I know that? Well, that comes from when our displacement graph inflects. So it changes concavity. So where it goes from concave down, in this case to concave up, at that point the curve inflects. That'll be when velocity would have a stationary point. And the reason for that is, and we'll see this later when we look at a bit more calculus, but possible inflection points always happen when the second derivative is equal to 0. So what we're basically saying is at that point acceleration is equal to 0. So I could translate that down too. So to get my acceleration formula, similar relationships. So velocity is stationary, so therefore I have I keep wanting to say x-intercept, a t-intercept. My parabola is going down, therefore acceleration is negative. Parabola is going up, it's positive. We have something like that. And if you think about it, the first graph there sort of looks like a cubic. So it kind of makes sense that when you differentiate it, you get something that looks like a parabola. And then when you differentiate a parabola, you get something that looks like a straight line. So these are some of the ideas which we'll look at in more detail certainly later on when we look at motion for today, 9J. We'll look at these ideas of rates of change and using calculus to solve the problems.